The 1 in 60 rule is a very helpful and useful tool in vectoring in air traffic control. In this video I'm going to explain what the 1 in 60 rule is and how you can basically derive it mathematically using trigonometry, using some basic trigonometry. 1 in 60 rule is short for a 1 degree turn over 60 miles will give you 1 degree of separation, or 1 mile of separation. What do I mean by that? Suppose that this dot represents the position of two aircraft that are directly on top of each other. They're obviously separated by altitude, but they're occupying the same space over the grounds, okay? And they're both going the same speed. Over 60 miles, they will both end up at this point. Yes, that's pretty obvious. But let's say that we turn one aircraft 1 degree. I know that's much more than 1 degree here, but just pretend that this angle is 1 degree. Well, over 60 miles, since the other aircraft is also going the same speed, that aircraft, well, the turned aircraft will end up here. The 1 in 60 rule says that if this change in heading is 1 degree, if they're going the same speed over 60 miles, the difference or the distance between the two aircrafts, okay, 60 miles ahead, will be 1 nautical mile. The cool thing about this is that it's scalable, so very easily. So for example, instead of this being 1 degree, if you made it 5 degrees, well then you'd actually end up with 5 miles over 60 miles. So if you turned one aircraft 5 degrees to the left, you'd actually end up with 5 miles of separation. If you turn one aircraft 10 degrees, you'd end up with 10 miles, okay, over 60. You'd end up with 10 mile difference between the two aircraft. 20 degrees over 60 miles would give you 20 miles here. Okay, it also works like this very easily. Let's say that instead of 60 we use 30. 60 miles divided by 2, that's why I'm cutting the lines in half here, is 30. Well, let's say that we turn somebody 20 degrees over 60 miles would give us 20 miles, but since we're only doing half of 60, which is dividing by 2, it's actually, we're going to end up with 10 miles over 30 miles, okay? So that's what I mean by it scales nicely. It's a very nice rule of thumb, and it's very, very accurate, I would say. So mathematically, we're going to use some trigonometry, basic trigonometry, to show why this is true. Very quick reminder, with trigonometry, we're going to use a right triangle. So we have a 90 degrees here. We have some main angle, which we'll call theta, and some other angle up here. In trigonometry, we have certain ratios of the sides of a right triangle, so everybody knows which side we're talking about. Okay, the side that's opposite the 90-degree angle is called the hypotenuse. The side of the right triangle that is opposite from the main angle theta is called the opposite side, and the side down here which runs adjacent or next to the main angle theta is called the adjacent side. Now the different ratios, well, basically what happens is this. If we look at geometry generally, okay, basically what happens, if we take a triangle like this, we take two triangles, this little triangle here and this bigger triangle here, if we take the length, if we take the opposite side, and we'll just call this the hypotenuse, which it is, if we take the ratio of O over H for the big triangle, okay, it will actually be equal to O over H for the small triangle because it's a ratio, it's something that's relative, okay? So that's basically, that is what a ratio is. It's showing exactly that. Okay, so there's just a quick little recap on some geometry. So in trigonometry we have different ratios, and they have names. So we have sine of theta, and there are like several other ones, but we're just gonna use this for an example. So sine of theta is, all this is it's equal to the opposite side for a certain angle of theta, okay? the ratio will always be the same for an opposite side over hypotenuse. And what I mean is, very quickly, okay, if we take a right triangle that has a very small theta versus a right triangle that has a larger theta, okay, you can see if we take the opposite over hypotenuse for this darker blue one, it's going to be closer to 1, okay, whereas if we take opposite over hypotenuse for here, it's going to be smaller, okay. So the ratio sine is dependent upon the size of the ratio, okay, is dependent on the measure of theta, or the measure of this main angle up here. So let's look at this problem in terms of trigonometry. We have one aircraft here, and we'll say that it's going to go 60 miles and end up here. We'll call this point A, we'll call this point B. We know that the line segment AB is 60 miles in length. We turn the other aircraft 1 degree. I know this is larger than 1 degree, but just pretend. So we have theta is equal to 1 degree. And we know that this is also 60 nautical miles. We'll call this point C. So we know that the line segment AC is also 60 miles. We want to find out what the distance is between line segment C and B. So, what are some things we can do? Well, number one, what we can do is we can basically split this triangle in half here, and we'll force a 90-degree angle so we have something a little easier to work with. Let me try to clear this out here. Okay, so this is now our 90-degree angle. So we know that if we can find the measure, and we'll call this point D, if we can find the measure of dB and just multiply it by 2, because this dB is the same as CD, okay, because we're just splitting this in half equally, then we'll actually have our answer what the length of CB is. So what we'll do is, let me redraw this right triangle over here. We'll go like this, okay, and we'll do this and this. Let's redraw points. We have A, I'm just doing this to make it a little clearer. We have C, and, or I'm sorry, that's not C, that's actually D, and we have B. Here's theta. Well, theta in this one, because we divided it by 2, is actually not 1 degree, it's actually going to be half of a degree, so we'll put that there. We know that the line segment AB hasn't changed, it's still 60 nautical miles, and we want to find out what dB is, okay? So we can just apply some trigonometry. What is, and by the way, our right angle is here. So 60 nautical miles, this length, AB, is going to be our hypotenuse, and BD, or DB, is going to be our opposite side because it's opposite of our theta, which is equal to half a degree. And so what we want to know is how many opposites are there per hypotenuse, because if we know that there are some number of opposites per one hypotenuse, then we just take that number and multiply it by 60, and that gives us the length of dB. So O over H, O per H, opposites per hypotenuse, is sine of theta, so we can write this like this. We have sine of theta, which in our case here, theta is half a degree, of 0.5 degrees. Okay, and what we need to do is we need to multiply that by 60, because if we just do opposite over hypotenuse, it's just opposite per one hypotenuse, and we want to find out how many opposites there are per one hypotenuse, but they're actually 60 miles. This is 60, not 1. But then also don't forget that dB is actually only going to be half of our answer, because we need actually to double it. So we also need to take this and multiply it by 2, which simplifies. If we distribute with algebra here, we have 120 times sine of half of a degree is equal to, and we'll get the calculator real quick for that. Let's bring the calculator onto the screen here. Turn it on. Let's make sure that we're using degrees and not radians. We are, so we're good there. Okay, so now we're just going to put this in the calculator. We have 120 times sine of 0.5 degrees is equal to 1.04718, etc. We will round that and we'll say it's 1.05 is equal to 1.05 nautical miles. So your answer there, the distance from CB, is equal to 1.05 nautical miles. And again, this is just kind of a little basic proof that of how you can derive the 1 in 60 rule. Very, very quickly, I'll show that it holds for other values of theta. Again, instead of 1 degree, let's use 10 degrees. Well, we still have the 120 times, but be careful. Well, it's still going to be sine, but be careful, it's not 10 degrees, because remember, we're taking the angle and dividing it into 2 first. Okay, so it's actually, if we use 10 degrees, we'll actually use 5, and this should give us a little over 10, and it does. And we'll do one more just to show, just to get a feel for it. 120 times sine of, let's say, 30 degrees, so half of 30 is 15. Okay, it should give us a little over 30, which is 31. So it's pretty close. It's a very useful tool in air traffic control. In the next video, I'm going to show some further applications of how to use the 1 in 60 rule.